concepts. How many of you have actually written a concept? Okay. How many of you think you might possibly someday write a concept? And how many of you think you might end up using a concept? Unbeknownst to you. Yeah. So we've now got this thing called a Concepts-Lite, Technical Specification, which means it's a document out there that you can refer to. It's sort of an international standard, but not mandatory. Okay, fine. Apart from the committee and a few people who kind of write blog posts, nobody really cares about that. What people care about is what can I actually use, what's available in my compiler. GCC, yay, it's now out there and implemented. Who's running GCC in production? Well, a bit tricky, but you need a time machine. But you can get pretty close. But most people are not able to actually play with and use and test in production the latest, greatest trunk version of a compiler. But you can play with it and have a little bit of a go. And hopefully soon we'll have some other implementations as well. People are working on getting a Clang version going, and the other one should come along. But there's enough out there, you can have a bit of a play and see, kick the tyres, open and shut the door a couple of times, see what happens and what are the consequences. Hey, wonderful timing. So I thought I'd start with a kind of retrospective. I was thinking about kicking straight off into concepts, whereas actually it doesn't really make a lot of sense unless you talk a bit about the context. What problems are we trying to solve? Why concepts? What are the alternatives? How does it stack up against the other ways of doing things? So I thought about C++, and it's quite a rich language. I don't think there's much debate about that. You could debate about too rich and which bits you'd like to take out. And we've got this distinction, quite an important distinction in C++, between what happens at compile time and what happens at runtime. And one of the things that I like about C++ is you can set things up so a lot of the checking happens at compile time. Of course, back in the day, when C++ was new, a lot of people were just very excited about being able to do object-oriented programming and use runtime dispatch. But things have got more complicated since then, for good or ill. So we've got at runtime, we've got this kind of class hierarchy, standard OO kind of things, polymorphism, you call a method, and at runtime it works out which actual implementation to go to. But we've also got templates, and as you know, if you trying to get templates and OO to jive together, it's not often a great success. They're approaching the sort of similar kind of problem, but in very different ways. And one major difference between these two, in terms of, if you kind of think about it at a slightly higher level, is actually to do with, currently anyway, with the syntax. In the first case, when you're using runtime and OO, there's quite a small set of possible places you could go when you call a method. You've got to actually have extended the base class. So you've got an inheritance hierarchy. You can't just have some random class out there that suddenly gets called when you call the show method. It's got to be part of that class hierarchy. And conversely, when you call the method, you know it's going to exist at runtime, because that's the way the rules go. If the method is pure virtual, you can't instantiate the object unless you provide an implementation in somewhere in the class hierarchy. So there's a kind of guarantee that when you call the method, something's going to happen. It won't just fall out into hyperspace. It's only the same with templates. With the second case, there we go. One of the beauties of templates and one of the pains in the neck is you can apply templates to unrelated types. And you'll kind of just, if it works, if it compiles, if the methods exist, everything's good, and if not, the other thing. I love technology. Didn't work. So, nothing to see here. Move on. Runtime polymorphism. Key component, you use the runtime type of the object, and it's been a fundamental part of C++ for C with classes basically since then. And the design hasn't really changed very much. Essentially unchanged for about 30 years. So if you take a book on how to write OO programming in C++, the kind of fundamental mechanisms, how it all hangs together and what happens, is basically the same as it's been for a very long time. And the nice thing about it in this context is if it compiles, it runs. To some definition of compiles and runs. But basically that's the thing. I'm still optimistic it's going to work eventually, but I think it's not. Oh no, there we go. Compile time polymorphism, on the other hand, has quite a few different characteristics. Sometimes also known as generic programming. It too has actually been in the language for a long time, but hasn't stayed quite the same for as long. Got more complicated. So the idea is you provide a template. Instructions to the compiler. This is how you write the code I'm going to want later on. And then at some subsequent point, you provide the necessary details about the particular types or non-type parameters that you want the compiler to generate the code for. And the simple use is when we started out back in the day, one of the great things about using templates is you can now have a type-safe list, for example. Everyone's happy with that. And that's the kind of thing you also get in languages like C# and Java with their generics. You've got type safety. Under the covers you might be doing some kind of casting back and forth. You don't know. The interface itself is type safe and you just provide different types, everything's okay. But then the first change was non-type template arguments. It doesn't have to be a type, it can be a size. So you've now got things like, I don't know, stood array, where you specify an instantiation variable, which is the size of the object you're instantiating. And as you know, if you've been around at all template method programming, you can now produce lists of prime numbers at compile time. What's not to like? Debug that. Well, maybe not. And also, as we've looked at in Marshall's talk, who was in Marshall's talk yesterday about deep learning algorithms? Yeah, a few of you. He was recapping and showing some of the techniques that people use. It's also known by other terms than generic programming, which is what you see when you get the error messages. And it's very, very hard, or can be very, very hard to debug what went wrong. You try to instantiate a template, and you get War and Peace on your screen. Who's seen that? Anyone seen that? Yeah. Good, isn't it? Very fun. Where do you start? Usually somewhere in the middle, yeah. We either start at the top or the bottom normally, and see whether either makes much sense. You're trying to get a hint really out of the compiler as to what you've done wrong. And the other problem with template code is it's quite fragile. Whether the code is valid or not depends on a whole bunch of stuff about the instantiating parameters, which it's quite hard to express reliably for the user of your template. And normally, when someone writes a template, they probably, but not necessarily, actually try to instantiate it once. Although, of course, they may not have actually instantiated all the methods, if it's a class template, but the likelihood is that they have. It's always a question, when should you turn something into a template? And people's opinion vary. A set of assumptions as the writer of a template about what kind of objects you're dealing with, what kind of types you're using, what methods the types have, and also probably some high-level assumptions about the semantics. Okay, so the class has got an operator less, but you're kind of probably hoping that actually does something sensible and doesn't write numbers to stand it out when you invoke it. It might, but again, those are the sort of assumptions you're thinking through. One of the problems with the instantiation bit is that if there is no valid instantiation possible of your program, because you've written something that can never be valid, the compiler is allowed to tell you about this. It doesn't have to. The reason it doesn't have to is it would actually theoretically be possible to solve the halting problem or something equivalent, because it's very, very difficult in general for the compiler to know that there can be no possible set of types, operators, etc. that you could conceivably ever provide to a template. So as long as you can end up with code that, when you look at it, you realise that there's no way that could ever possibly have compiled. So it can never have been instantiated. But the compiler's been happily parsing it and just saying, yeah, fine, whatever, for quite a while. So this does make life a bit more difficult for us. But then, that's what it has. So library writers tend to rely on documentation. What's the problem with documentation? No one ever reads it, yeah? Any other problem with documentation? It's wrong, yes. And also, I can read documentation, sometimes I do, but the compiler can't. So you're now expressing the same thing in two different ways. One way in English text, another way in code, and they don't necessarily say quite the same thing. Another problem is, as I mentioned before, the diagnosis of the problem is quite painful. So into concepts, at least that was one of the theories. When one of the earlier papers that came up, the phrase was, concepts introduce a type system for templates that made templates easier to use and easier to write. So that was the kind of one of the driving forces behind adding concepts to the language. That was 2006. That was actually quite late in there was quite a few papers before that, but I thought that was a particularly good statement of intent. There's an earlier paper from Biana, 2003. That's just a couple of years ago. Yeah, a while back. It's taken a while. And one of the reasons for that is just because it's actually a lot more difficult than people thought. Currently in C++, templates aren't constrained at all. So you can provide basically any possible type, whether it makes sense or not. And the compiler does its best to turn the template definition you've written, plus the types you've provided, into some code. And if you want to do anything cleverer, you've got to get in to the type checking that the compiler does with the actual syntax of the method instantiation it's doing. So you've got a template, a class template, inside of which is a method, and inside the method there's A plus B, and the types of A and B depend upon the template parameters. So the compiler looks at A, looks at B, looks up possible overloads of operator plus, looks at what the return type is, looks at where, and that's all done instantiating the template. And you're quite a long way away from where the template was written, and you're possibly quite a long way down the call stack. So it's very hard for the compiler to kind of know who to tell, so to speak, that there's a problem. It could be a problem with the writer of the template has done something that it doesn't really make sense. More likely it's a problem with you, the user of the template, that you didn't realise you needed to provide an accessible operator plus for the two types. So, I thought to start with a very, very simple example. Sum. What do you think sum does? You hope. It probably adds together A and B. But it doesn't really tell you anything about what appropriate types are for T. What can I provide? How can I tell? It's a trick question. You've got no idea what goes on inside sum. All you've got is the declaration of the function. Try it. Yep. You can try it and see what happens. Read the documentation. There's actually there's two questions that I hinted at earlier. You've got the first one, the syntax. Will it compile? And the second thing is, will it do what I expect? Concepts helps a lot with the first one, doesn't help quite as much with the second one. Perfectly good reason, I'm not sure how to do much with the second one. So, we have some class with something happening inside it. We write a test function that takes x1 and x2, and we call auto value sum, x1, x2. Will it compile? Is it valid? Well, we don't know. We can't tell whether it's valid or not with that fragment because we don't have access to the full implementation of sum, and that's the only way we can check currently whether that's going to compile. Which means a couple of things. First of all, you have to break all the encapsulation. You've got to poke around inside the implementation to see whether that code is valid. Which also means you've got to have the implementation, or the compiler has to have the implementation available somewhere, which again makes it part of encapsulation stuff. Also, if you change the implementation, oh dear, suddenly you now maybe are calling different methods inside the implementation of sum, and what used to work now stops compiling. And there's no real hint about that from template type name T sum, TA, TB. And it's always a problem with the standard library, where the standard specifies quite clearly what the method signatures need to be and gives a kind of as-if explanation of what happens, but doesn't mandate, and you shall write the following code in your template. So you can end up with code that compiles with one standard library and doesn't with another, because one person's requires a default constructor and then copies it somewhere else, and someone else does, I don't know, a sign operator in implementation of the same method. And so your class may or may not comply with that. So currently you end up with lots of documentation. If you've looked inside the C++ standard, you get things like this, which I just nicked out of the last working paper. Table 718, less than comparable requirements. And then you've got a list of things. There's an expression, typically a list of expressions, something about constraints on the return type. It doesn't have to be bool, it's just got to be convertible to bool. And then some of the higher level requirements. So in the case of A less than B, if it's less than comparable, the idea being is it's a strict weak ordering relation. That's a bit trickier for a compiler to check. You can't really. So you still need this sort of semantic information, whatever you've got in any language, to explain what the kind of purpose is of the function and what the implementation is supposed to do. But this sort of stuff is much easier for a compiler to check and to find, again, the concepts are a way of specifying something. But the problem is, I thought I'd do a quick example of what happens. I have a class X with nothing in it. I create a standard set of X's, and I call x.insert with a default constructed object of type X. And depending on which compiler you try and what warnings levels you have, I get somewhere between 50 and 100 lines of error message out of those 3 lines embedded in main. That's not good. All they're trying to tell me is that I need to have a less-than operator for X. And some of the best compilers use all sorts of clever tricks to give you a hint, because there's somewhere in there an assert or static assert or something that has the words less than comparable or similar in the message. But it tends even so to be a bit buried in lots of other guff. Of course, it's possible that code would become valid if the paper about default comparison operators makes it through. But at present, that's not valid code. So I thought I'd start with a very simple example of a function taking int, check. Whatever check does, I don't care. And I can write code using this function down here, int main, 2 ints, call check against it. That will compile. Anyone disagree? And it will run. Whatever check does, I don't care. As long as check's a valid function, I can call it. And the prototype guarantees that I've complied with the contract for calling check. Straightforward, simple, nothing to see here. Which means I don't need to ever look inside the implementation to see whether it's valid code. I might want to look inside the implementation to see what it does, but not to see whether the code is valid.
Would you put warnings in return of a full int main?
It's perfectly valid. You might get a warning. Some compilers do. Type conversion, that's always good fun, isn't it? So I accidentally, or perhaps deliberately, called check with E and pi. So what happens? I provided a couple of double values and I'm calling a function that takes a couple of ints. I may get a compiler warning, but it's perfectly valid C++ code. What's it doing? What am I actually calling check with? 2 and 3, yep. So that's probably not what I actually wanted to do. It may be, but likely not what I wanted to do. And that's the problem. Oh well, I know how to fix that. I create another overload. Takes a couple of doubles. And I write another implementation. There's a certain similarity between these two implementations. But copy and paste is our friend, right? So it's easy to solve. So I've now generalized the function to a predefined set of types that I chose, but duplicating the implementation. So there's a couple of problems. The first is, how many sets of types should I pick? And the second is, I've got to duplicate this every time. Solve my problem, though. Or I can generalize it using templates with existing code. I just change the type parameter to some type name, generalize that. I haven't had to duplicate the implementation. Obviously, return LHS equals RHS is not difficult to duplicate, but in general, they could be quite a lot longer than that. And now I've produced a set of functions for an unbounded set of types. I've got no control over all the possible types that this function now might be instantiated against. I probably had in mind my use case in int double double. But now, of course, I can call it with string and char const star, or foo and wibble, where foo and wibble are some class in a program I've never ever seen because someone else borrowed my code. Slight aside, you've also got to think a bit possibly about whether you want to take it by value, by const ref, or by forwarding ref. And the best answer may depend upon the type. Is it easy to copy or not? Will it fit in the register if you're really worried about kind of latency constraints? And I'll mention that again later on. That's probably what I'm going to say about that. So I can further extend the template by saying, well, actually, sometimes I want to call this function, and I don't want the types to have to be exactly the same. And one of the things about template lookup is a near match isn't going to be good enough. So I'll generalize it, and now I can take two arguments of different types, which is cool. But any compilation problems occur quite late on in instantiation time. So down here I've just copied and pasted some of the error message that I got when I called it with a couple of things that it didn't work with. So I passed in, the first argument was an int, and the second argument was an int star. You can't compare an int and an int star, so the equals equals call fails, and I just get this thing in instantiation of the function t ref ref and u ref ref with giving the types can't compare a pointer to integer. Well, the obvious thing is you turn on the permissive option and it compiles now, right? Fortunately here it does actually show me the line of code, and it's very simple, but if that was a much bigger template, it's going to be quite tricky. But I'm sure you know all this, so let's move on. Can we do better with this second argument? What do you think? It's C++, you can always do better. Whether you can understand what you've done, of course, is the second question, but we'll come to that in a bit. I want to constrain the template. When the function template is called, invoked, you've got overload resolution to find which is the right version of the possible overload set that I want to call. And then the second bit is now go off and instantiate it. Handling a bit, it's slightly more complicated than that, but basically you've got those two stages. So what you want to do in stage one is to say, well, ideally, I don't want the function to be even visible in the overload set if it doesn't make sense to instantiate it to these two types. So just hide it. So I can call check with int and double, and it'll do the right thing. But if I call check with int and int star, then it won't even be in the list of things I can call. Doesn't make sense. So enter spin A. Who likes spin A? We can ask that before in the week, I think. Yeah. Oh, jolly good. Let's hear it as a spin A. Who can pronounce it reliably after a long night? Substitution failure is not an error, is what it's short for. Which means when you're instantiating a template, particularly for the purposes of name, lookup, overload resolution, if you get an error, what would be an error were you to proceed with instantiating it, it's because you're substituting the types in. It's not really an error. The compiler just unwinds and says, I won't go there again. And it's the basis for things like enable if. Who's used enable if? A few people. Who's heard of enable if? A few more? Yeah, good. So here's a nearly trivial example of spin A. So what I do is I've got my type name T, unconstrained, type name U. Default value for that is some sort of value type based off T. Got my template here that takes two types the same. I've got int main. I call the function twice, once with two integer values. So what it's going to do is going to find, oh, there's two possible f's, that one or that one. Substitute into this one, and I'm getting type name U, type name T, it's a bit messy. It's actually ends up non-viable. For the second example, I pass in a vector and an integer, and it looks at the two. Those are not the same type, so that disappears exactly that one. So you can use some sort of compile time technique, and the one you don't want just doesn't appear at all. Of course, there is a problem with that. If the function you want doesn't appear at all, what error message do you get when you try to call it? Just, I can't find this function. You don't get told why the function you wanted to call can't be found, which is a slight problem with some of these techniques. So alternatively, you can do something a bit more complicated. You can actually include, I call it magic.h, we'll come to it in a minute. That's where the magic comes. And then I add on this bit in yellow. I've got these types T and U, and I put in an enable if T, they're equality comparable. So, what's happening? I'm saying I've got a template that takes three template arguments. The first two are deduced by the arguments I pass in to check, LHS and RHS. And the third one is not even named. So there's no possible way really of kind of providing it or looking at it. Okay, well the compiler says, okay, you need this thing, I'll look up, I want to do a split enable if T of these is equality comparable, T and U. So it goes off, does some magic under the colours, which we'll see in a bit. Decides whether or not that makes sense. If it does, you've now got a type here, and if not, you've got effectively a compilation failure. So that function just gets eliminated. And it has the desired effect of removing it from the overload set. So as I say, you just get no matching function. If you're lucky, you get a list of possible candidates that you might have met. So at least you can say, okay, I didn't get to call the function I thought I was calling, and this is the reason. Template argument deduction failed. Rats. So it doesn't really help very much with knowing exactly what I've done wrong. Again, compilers vary, and depending on exactly what you do and how clever you are with this, you can get some slightly more meaningful results out. And inside magic.h, which I've got a very simple example of something I've called is equality comparable. Very often, some of these things are available in the standard, and some of them will become available, but they're not that difficult to write. Online, you can tell. This sort of stuff, who has kind of cold feeling around the back of the neck when they see code like this? Yeah? Fortunately, you can hide it in the header and give it a nice name like magic, and then no one ever looks there. So we can do this stuff, and I'm sure most of you have seen this kind of technique before and probably know better than I do, but it's got a few problems. It's not for the faint-hearted, it's not obvious, it's not very easy to write. Copy and paste tricks, working examples, modifying stuff, using other people's libraries that include it is quite good. But it's quite hard to read, make sense of. We should be able to do better. There's also a problem with my magic.h because of the rules. In here, buried in the middle, I probably should put it in yellow, that's the actual test that I'm trying to do. My template has LHS equals RHS. What I want to say is that valid? But I can't write that currently inside this sort of syntax. I've got to find something that can be evaluated properly in a string-like context. So I have to take use decal val, make sure it's of type tref, generate a kind of pseudo object of that type, test that that's equal, and then do decal type as an expression involving that. I mean, it's all messy, and there's multiple ways of doing it. That's just one way. But we've come a long way from the expression I really wanted to validate. And in some cases, it's quite tricky to work out what to write here. You can't just copy and paste the syntax from the template. That basically is what I just said. So, there's a white horse appearing with concepts on it, solving all our problems, or at least some of them. So I thought I'd look at how solutions involving concepts, and we've spent, what, half an hour getting to this point, covering stuff that, who's seen something particularly new? Yeah? Most of it's just like revision, but I thought just kind of, and thinking about it, hopefully thinking about it in a slightly different way. What are the constraints in terms of writing code at a high level? How does concepts help? This is the sort of problem that we've got ourselves into. What can we do about it? So, templates are typically, not always, typically used much more often than they are written. So, how does concepts help with using things, and also does it help with writing things? And I'm actually much more concerned about the using than with the writing, because it's hard to write things. If people have to spend a bit more time and thought and care, that's less of an impact than the many people, hopefully, who will use a template. So the first way of doing it is with this requires syntax. New syntax. You might think your eyes have gone a bit funny because requires appears twice here. That's just a shame, and might possibly go away before we get this thing finally into the international standard. But you basically add something into an existing template. So I've got the template as we've seen before with T and U, and that's exactly the same as before. But now I just add this extra line in. It requires that if I, this is sort of function style, if I had a function that took a T and a U, that is valid code. Now the beauty of this, compared to the example with enable if, is that's exactly the same line of code that I've actually got in my template. So it's not difficult to work out what the requires expression should look like. It matches the code in here. And also, the compiler now knows what I'm trying to do. It knows I'm trying to constrain something. It doesn't think I'm trying to do some clever overload resolution, and just by chance it happens to end up as doing a constraint. That's the purpose of requires. So it can tell me that the constraint's not satisfied. Much clearer indication that what I've done wrong. It's your fault. You haven't complied with the constraint that the writer of the class, or in this case function, wrote. So I don't ring up the guy who wrote the library and say, your code's broken, because that method tells me that it's me that hasn't satisfied the constraints. Which even that simple thing, I think is a great benefit. I know which side of the fence the problem is, and it's my side, as the consumer of this function. But again, could we do better? We can name things. Names are powerful. As we heard earlier in the week, one of the talks I was in, the problems with computer programming, two problems, cache coherency, off by one error, so maybe look up. Names are difficult, but if you can name something, you can express in semantics. It's not obvious from just random bits of code. What, again, the high level, what's the purpose of this constraint? What am I trying to express? So if I name it equality comparable, that says something to me. And also expresses possibly some of the other expectations about equality to do with its behaviour as an operator, being reflexive and symmetric and all that kind of stuff. You can also share it, write it once and use the same name concept in multiple places. So you don't have to parse a whole bunch of C++ when you see the requires expression. You've just got a name for it, and once you've understood it once, you understand what it means in all the various contexts. So it's got definite advantages. So you can write it out like this, and have to provide, of course, the definition of what equality comparable means somewhere. And now I also get a much more helpful error message because it tells me concept and then the name of the concept that's not being satisfied. So that's now looking like something that makes sense to the user of the function when they get a compilation error. And Andrew's got, I don't think it's in GCC trunk yet, it might be, but he's done some further enhancements on how to improve the error messages that the compiler gives. So he wrote an article for Overload a couple of issues ago, where he gives some examples of using concepts and shows some error messages that he actually managed to genuinely obtain out of his little branch of the compiler. One of the decisions that was taken was, well, we've got function templates, we've got now new shiny toy, variable concepts, because we can use variable templates. What's not to like? So we can now declare a variable called equality comparable as an alternative syntax. And write some slightly different syntax in here. That's very, very similar to the previous example. What you've saved is you don't have to write brackets. Does it matter? Don't know. The other thing, of course, is that functions overload, variables don't. So if you write a variable concept, you can't overload it. Does that matter? Well, it's hard to tell, isn't it? Because you start out and you write a concept and you start using it, and it's not possibly until quite a long way down the road that you suddenly realise that for a particular use case, you're going to need to have some sort of specialisation of this concept to cater for. I mean, a very common example is when you do stuff with numbers, and then as John said, you suddenly try doing it with a standard string and a char constar, and you realise you've got a special case here that you want to do something different with the case of a string literal and a stood string. So you might want to overload your concept for that particular case. And if you've gone for a variable concept, you've got to go back and change it to a function.
By the way, just to clarify, the reason I said string before, I didn't realize you were talking about an integer concept. I thought we were talking about a container. I now realize that we've gone beyond that. The reason I suggested a string is because it involves memory allocation. So once you have into double, then you go to something that does something with the heap, then everything could break, even though before it worked perfectly.
Yes, yes. As you say, string's got other things it does under the covers. If you've got a long enough string, you're going to have some memory allocation and stuff like that. Things about ownership and stuff like that. Maybe you could use a shared pointer or something to see what it does with things with ownership constraints. All I've written though so far in my equality comparable is I've just checked it one way. T is the same as U if I write T equals U. But it's not really very general. For a proper equality comparable constraint, I'm going to want to add in T equals U, U equals T. Oh, and there's a not equals operator, isn't there? So it probably makes sense to do the mixed set. So I've now got 4 things in my constraint. And if you look in the ranges TS, working paper for that, you'll find they've written a whole bunch of concepts, effectively specifying in code what the existing library specifies in those tables that I showed an example of. And they've got something very similar to this, quality comparable, capital E, capital C, which requires these 4. Problem is, of course, this now means in order to satisfy a quality comparable, my classes have to be able to sort of do all those 4 things. So I've now made the job of using a function that uses equality comparable more difficult, because I can't just implement one operator, I may have to implement multiple operators. So if I now take my little stock test, and I've written an operator equals equals in it, and I call foo, and I now call check, and I use equality comparable from the ranges TS, I get a failure, because I don't have a not equals operator defined. All it still says is concept equality comparable isn't satisfied. I think, what do you mean? I've written an equality comparator. What more do you want? And that's one of the things where I think it's a little bit tricky to know how it's going to go. If you've got a complicated, requires kind of constraint, particularly one that inherits constraints from other places, the compiler can tell you you failed to comply with this constraint. It's not always obvious what I need to do to change. Which bit?
Surely it comes down to here. Equality comparable is the wrong name. It should be either asymmetric or symmetric equality comparable.
Yes. So that's where it becomes interesting. Because how tightly do I want to couple my kind of concepts to the precise implementation details of my function? So in this case, I'm calling it with 2 arguments at the same time. But supposing I call it with test and wiggle. The implementation of check, it might make sense to write it one way around, it might make sense to write it the other way around. I'd be a bit unhappy if as an implementer I couldn't just change the order of the comparison because it wouldn't satisfy the constraint any longer. So yeah, it's not an easy one. And one of the reasons why it didn't happen in the C++ or X stuff when they're looking at the concept stuff actually enforcing what you could use in implementation was you end up with lots and lots and lots of subtly different concepts if you weren't very, very careful. However, you can always cheat, which is a danger. The concept requires a not equals operator works, but actually the implementation, I just had a look, doesn't use it. So you can end up declaring it and not defining it, or doing it as a free function. So now I'm lying to the compiler. That always ends well, doesn't it? And again, that was an example of just both types being the same. If I do it with 2 types that are different, so I've got a test that has an operator equals with it, I can call check v, 0, and looking at the code that's inside check, it's just going to do a check that that argument equals that one, so it will work, but I haven't complied with the concept. So I'm going to have to go and write 3 functions, and even worse, because they're operators. Some of them can be defined in class and some can't, because I've got an int on the left-hand side, I can't put it in my own class. So it's a bit messier. So one of my kind of questions, I guess, about the way the ranges TS is going is it is making types more regular. Because if you want to use some of these concepts, you're going to have to make sure that when you write a type that wants to be equality comparable, you have to make sure you provide the whole set of operators that concept requires, or functions in general. And you can argue, is that a good thing or a bad thing? It depends. It's quite nice to have things that are regular and all behave the same way. But as we all know, the problem with theory and practice is that in theory they're the same, but in practice they're not. It's often nice if everything's regular, but every now and again you come across a case where you really rather it wasn't. And concepts like enforce a certain amount of higher level of regularity and things behaving the same way.
Sorry.
Yeah.
Wasn't there somewhere, I can't remember there being a headline where if you gave it an operator less than that was correct, it
Yes,
or the other
yeah,
one.
reloads. So you could do something like that. And again, it's possible you could go off and write some constrained templates that would generate that lot for you. But it does make it slightly more complicated.
I guess there's also the example of Lua, which tried to do that and then ended up trying to having to roll back on the equalities because for some types, for floating points, not nans that can be the same and compare not equal.
Yeah. Yes. What you do in nans and equality is always an interesting question. And there doesn't seem to be a right answer really for that one. So you've got a choice really with concepts. You can either write a named concept, and that's got a lot of benefits. It's got a name, so you can attach semantics, you can reuse it. But on the other hand, it then means you're potentially over-constraining every function that uses that concept because you have to comply with all the things in that named concept. Or you can go off and use the kind of native raw requires syntax, and then every single method you call has a list of C++ syntax that you have to read to understand what the concept's trying to achieve, and you've got no names to help you with meaning. So that seems to be the kind of design constraints, the design space we're in. And I think it's still, well, as far as I'm concerned, still too early to tell which is the best way to go in any given case. There's a question at the back.
Can we define two concepts, the equality concept and the inequality concept, and then just use?
Yes. You could have a more refined concept.
Since we know the implementation only requires the equality, we can just require the equality, and then if we change the implementation, we can also require the inequality.
Yeah. So in this case, we could have, or the previous case, we could have two concepts, one with equality, one with inequality, or as you have one for the symmetric, one for asymmetric, but then you end up with a multiplicity of concepts. So I don't think it's going to be something that has a really simple, obvious answer in all cases. But it's a lot simpler to write than the alternatives. All that enable if stuff does your head in. It's much clearer to understand, I think. The error messages seem to be quite clear. As I said earlier, it's a lot more obvious whether it's your problem or the template writer's problem, which is a good thing. I'm not awfully happy with requires. Just seems a bit silly. There is, I think, going to be a paper in the pre-Hulu mailing. Both Andrew Sutton and Richard Smith have muttered about trying to rewrite that particular bit of syntax to make it a little bit simpler, which I think would be a very good thing. And I'm also not really sure about why do I have to write bool? Concepts can only be bool. Why do I need to specify that? It's not really required. I've got to specify it has to be bool. Really? And all the kind of fluff around it. So there may well be some movement. There are a lot of people who are trying to think about that sort of stuff. And having both the function and variable form, again, I'm not really persuaded it solves any problems I've got. One of the differences, who was around some years back when Herb did I think it was a keynote on generics, templates in sort of C#, C++, Java, and looking at what was kind of the same, what was different. Anyone around for that one? It was a very good summary. I remember he started by saying, I'm going to boot Linux on this box, don't tell Microsoft. One of the differences between C++ templates and generics in both C#, Java in general is that we tend to go for very much, if it compiles, it works in C++. And as I said, there's no requirement that the types have to be related, which is both a great strength and the other thing. But the more closely the instantiating classes are tied together by having to implement the same interface. It also prevents all sorts of optimizations that can be done, because the net result in C# and Java is that the underlying implementation is basically the same. It just calls different functions at runtime, and waiting slightly. But constraints are still very much in the C++ camp. All you have to do is provide a class that will satisfy the following list of syntax. It doesn't enforce any kind of class hierarchy stuff on it, or that you have to implement particular methods. You just have to have certain syntactic expressions available. So it does fit well into the C++ world from that point of view. Now I thought I'd look a little bit further. What happens with more complicated? Sorry?
Question, did you just say it's not possible to check if a certain method exists in the template argument?
Oh, you can do stuff, in a constraint. You can require that particular expression is valid. But unlike with an interface-based design where you're saying it's a virtual method that I'm implementing in my class, very often you just have it's a bit of C++ code, it must compile. Whether it's like an operator, is it a free function or is it a member function? I don't care. As long as the code is valid, it doesn't matter how I got there. Whereas in the C# and Java world, you're saying, I implement this interface, and therefore this method has this signature. It's in our world, either const or non-const. These are the overloads, these are the types. Whereas with the kind of constraining world that we have, we're saying, this bit of syntax works. I can write A equals B. Now, it may be that actually there's an implicit conversion going on somewhere and there's another operator being called. So it's a lot more fluid and flexible than the interface-based solution. Does that make sense?
Yeah, you can also call methods of the template argument that you get.
Yes, you put methods in. I've just done it with the equality operator, which maybe I should have done more with the methods as an example as well. So what I was thinking about was, when you've got multiple function templates and you want to be able to pick the right one based on information about the types that you're instantiating with, that does get very complicated. And it's particularly difficult in C++ currently if you start using enable if. So possibly an example may help. So what I'm trying to do there, I've got a little class V, and I want to construct it from two different sorts of values. In the first one, I want to construct it from something that's int-like, and in the second case, something that's float-like. So I think, I know what I'll do. I'll write a constructor that takes an int type of object, and I'll put an enable if in as the second template argument. So this only works if it's an integral type. And the second one only works if it's a floating point type. Okay. I think we all understand, I hope we all understand what I'm trying to achieve. Does the compiler understand it? What's the problem here? Anyone know? Anyone come across this one? Yeah?
There are types that satisfy both, and you get overload resolution problem.
Yeah, there's a couple of problems. One is that you want to have a type that might satisfy both. In this particular case, there's an even more fundamental problem. It looks up, you call a constructor with something, and you've got two constructors. It doesn't care about the name, float int. The primary argument, there's only one in terms of which constructor you're going to call. They're ambiguous, completely ambiguous. Whether or not it's actually int-like or float-like or not, you can't even compile that without even trying to instantiate. So there aren't any problems that you can't solve without more arguments. What you have to do is find a way of making those two constructors look more different, so the compiler can work out which one you meant, and then you throw away the extra cruft you added to make them look different, to make them look the same again. If you use enable if, that happens quite a lot. And the problem you get is with the existing example, I just get a straightforward failure, error. I've already got a constructor that takes a single template argument. It doesn't bother to look at the other template arguments. It says you failed on the first one. The fact that the second one is different doesn't matter. So there's a well-known technique for doing that is you add a second argument to resolve the ambiguity, and the second argument has a default value. You never actually provide it. The compiler provides a default value. You rely on spin A to say, oh, but the default value makes no sense in this case. So the thing you're going to create, just throw it away and don't bother. You're going right around the houses just to get back to something simple. So you might, for example, just declare a struct called something helpful like dummy. And then I add a default argument to my first constructor and my second constructor. And now when I provide one argument to the constructor, the compiler synthesizes the second argument, and dummy1 and dummy0 are different types, so there's no ambiguity. So it tries both of them, and it then says, oh, but there's a second template argument, oh, but it doesn't work because it's not integral. So it throws away the whole of that one and is left with this one. I'm never quite sure with code like this whether to stand back and think, wow, that's impressive, or wow, that's just crazy. And it does make doing overloads, multiple overloads with existing technology very difficult. And also, you are kind of hoping that the compiler is going to throw away all these dummy arguments, but it's possible it might not be able to. And you've lost what you're trying to do in the complexity of the implementation. And of course, you do actually have two template arguments now in your constructor. It's no longer a constructor that takes one argument. What is the default, admittedly, but it does actually technically take two. So there are a lot of other problems that you might get into if you happen to have other constructors that take two arguments. It could get a bit messy. So with concepts, it's much simpler. The reason being is that the constrained arguments are different types, and the overload rules have been made more complicated. That's a shame. But hopefully to make things simpler. So the compiler is perfectly happy if you have two functions with the same number of arguments and just different constraints on the types. That's perfectly okay. So you don't need any dummy arguments. And that seems to me a clear, definite advantage of constraints. So here I just go, rather than having something that is an extra template argument, I add in a require statement. And here I add in a require statement. So I still have two constructors, both taking a single argument, which is just some named type name. But the compiler is happy to overload on the constraint. So all the extra cruft I had to add to get it to work disappears. And I'm now expressing much more clearly the intent. And it does what you expect. And I haven't got to worry about whether the optimizer is going to get rid of the default argument and how to kind of do all that stuff. And again, in C++17, you can make it slightly simpler too, because there's a set of variables rather than like a slide. Here I've got all listed as integral kernel value, and in 17 you can make it slightly simpler by just using single phrase here. So again, I think that's quite clear, quite easy to read. Well, I think it is.
Can you have multiple requirements?
Yes. You can have multiple requirements, clauses. And again, one of the questions I haven't really had time to play with is whether it makes any difference to compilation times, which order you put them in. Because some of them are going to be easier to check or will fail more often than others. And one of the comments that Andrew was making was if you've got a complicated list of requirements, ordering it right can make a difference, quite a significant difference, to how much effort the compiler has to spend in checking out which constraints are satisfied. But yeah, you can have quite a few. Again, I've tended to go to take simple examples.
But is the standard going to actually specify which order they're
yes.
in, or is it going to be implemented?
It always works down the list of requirements. So a bit like with short circuit evaluation of Boolean expressions, if you've got a constraint further on that you need to have something else satisfied first, you put the something else at the beginning. So the order is well defined.
So if you put multiple requires everything implicit and separated, I think.
Yes,
Is it possible to do more as well?
you can do both conjunction and disjunction, yeah, both ands and ors. And there's a whole set in the TS explaining kind of what that means and how it works. And one of the, that's one of the areas where the performance of the compiler may prove to be a bit of a problem. If you have a couple of ors at the beginning of your list of requirements, then you may end up with the compiler having to instantiate a whole lot of stuff for every single type that you try and call this function with. Again, I'm not entirely sure how you're going to be able to get that information out of the compiler. I'd like a sort of hint saying, that's not a very good way of writing your requires clause. But there may be statistics you can get out of the compiler or something like that, or you can guidelines that will appear. Mostly, I suspect you're going to have fairly simple requires clauses, and it just work.
Can you reference requirements? I mean, suppose your template uses another template which has requirements so that you can have a kind of chain of requirements that you use.
Yes, you could do that. But again, if your template calls another template that has requirements, then the compiler is going to enforce all the requirements up the chain are there. But you might prefer to have the requirement at the top level to avoid the sort of stack of errors that you can get. I didn't have a chance to play with that. So it simplifies overloads, makes it much easier to overload between pass by value and pass by reference, which I mentioned earlier on, because you haven't got the possibility of because the requirement is part of the signature. So the compiler looks at the requirement and says, you've got a primitive type, so you've got an overload here that passes by value, or you've got a user-defined type, an overload here that passes by reference, and it just does the right thing. So I think it's a more powerful technique than what we've currently got. If that wasn't enough syntax, I've got more. There's a concept introducer syntax and an abbreviated syntax, which I haven't yet demonstrated. Bet you can't wait. It adds a lot to the complexity of the wording, and again, I'm still not entirely persuaded we need 3 or 4 different ways of stating effectively the same thing. But I think the jury is still out a bit on that one. So let's use the template introducer syntax. Up here I have got a couple of named concepts. I've got int and float. And I've used the variable concept format, so there's no brackets involved. So I've just said this one here is true and exists, it's valid if it's an integral type, whatever t is. And then down in my example with the 2 constructors, I don't bother to use the word type name, I just put the concept name in there. Int and float. Is that better or clearer, or is it worse and less clear? Is it more complicated? Why do you have 2 ways? What does it mean if I see some code written one way, some written the other way? Not sure.
Can you specify multiple concepts with this syntax?
Sorry?
Can you specify multiple concepts with this syntax for type?
Yes, I can put multiple things in here. I've got a couple of examples of some of the constraints on that, which I'll come to.
Can you also have a requires clause?
You can also have a requires clause, yes. And there's rules, again, in the TS to explain what the ordering is between the implicit requires clause in here and the actual required clause in the... I think that one comes first. I can't remember the rules offhand. You've also got complexity because what you might have in here could be constrained as well. And then you've got a requires in here and something here which actually happens afterwards, but you know, hopefully most of the time it won't matter because the ordering is not that important. But it is all just syntactic sugar. There's a kind of rewrite rule that says if I write that, it's equivalent to writing that. And that's how the rules basically work for working out what the order is. You write it out longhand, and that's the ordering that the requires clauses will be satisfied in. Bit of a side channel, there's a long discussion that was had as part of the wording as to when things are actually genuinely equivalent. So could I have both of those in a header and it would be valid code? And when things are functionally equivalent, I have the same effect, but aren't actually equivalent, so you couldn't have them both in the same header. Which does your heading. Fortunately, most of the time, you only write them once anyway, so it doesn't normally matter. But it does save a few characters. In this case, 37, not 58. Is that good or bad? I don't know. And the abbreviated syntax, you don't bother with those nice less than and greater than symbols. I just say V takes an int. Okay, pop quiz. How do I know that's a template? You've got to find int somewhere. There it is. You say, oh, it's a concept. So you've silently introduced two templatized constructors here.
Do you care if it's a template?
Do you care if it's template? The answer seems to be, some people do and some people don't. So depending on who you talk to, some people think, this is magic. This is what C++ should have been right from day one. And other people go, I don't know, what do we think in the room? Who thinks this is brilliant, that you don't need to put all that horrible syntax with nasty brackets and stuff, and you just get templates straight out of the text? Who thinks it's horrible? Who thinks it's both? Yeah.
You need export.
I'm still wondering about this one, I must admit. My biggest concern is not so much when you're sitting inside an existing code that compiles and I can run. My problem comes, a lot of my day is spent doing code reviews on the web with fisheye or something like that, and all I've got is a little bit of code out of context. I can't compile it, well I could, but it would take 3 hours. I've got to find where that thing's defined to know whether I've got a template or a non-template. Does it matter? Well, it might do, because the overload rules or lookup rules for template functions and non-template functions are subtly different. So things like the types have to match exactly for a template, but you can get user-defined conversions, more of them in for a non-template. So it might matter for reading the code.
You can implicitly introduce a T symbol as open, as you write like that. You can use T insert.
Yeah, I can put a name in there, I just haven't named variable. I mean, can I have a template type?
Yeah, the T
U.
inside the book of the insert.
It's
real type there.
Int is the name of the type, so I could use int inside here.
Can you go to the explicit, the actual type, or just the concept?
Well, it will populate that with the actual type when it instantiates it, so I have got it, yeah. Oh, any other question?
I think everything I've shown so far compiles with the latest GCC. Does that not compile as well?
Yep.
Oh, I should have had it on.
Yep. I think it did anyway.
Because it's kind of confusing. Because if you look up at the top, you've declared, it looks like you've declared it into full.
Yes, yeah, you need to notice that concept bit is quite important. And that's my biggest problem with it, is you need to know more context to know what this means.
How do you get a D inside
You haven't got a T any longer, no. You've got this name type, int. I haven't given the variable a name, probably should have done. But I've got this name type int, which happens to be a constrained type. So all I know about int is, when I write the code, is it will be something that's integral. When I actually instantiate this with a particular type, then inside here, if I use int, it will get the actual type it used.
You can never do that.
So I couldn't have well, struct itself is not a template, struct itself is just a regular struct. I could make struct a template as well. All I've got here is two templatized constructors. Well, I could templatize the struct itself, but as I'm sticking with the simple case of functions. Well, that would be enough for an hour and a half. Couple of other questions?
What happens if I had two concepts named int?
Two concepts named int. Well, in this case, this is a variable concept, deliberately, because you can't overload variable concepts.
Right.
So it's unambiguous, but yes, if I had multiple concepts or multiple overloads of a concept, or if I happen to have, poor choice of name, it would depend on what header files I'd included before this, what that meant.
Is it in a namespace?
It can be a namespace. Yeah, you can put it follows all the same rules as any other type, so you can put these things in namespaces and do that sort of stuff with them. Question from the back?
Can you still specialize that?
Can you still specialize that? I believe you can. I'm not sure I want to try. You waive the right of syntactic sugar. I mean, under the covers, it still writes out longhand, and I think the next slide might even show that. Yeah, that's the question. Yes, no, or maybe about whether it's a good idea to even try this. It's a couple of slides further on. So you can always write out this short form in long with all the template type name and requires clauses, and then you can do all the normal things you'd be able to do to specialise it. I can't remember offhand whether you could specialise the short form. I just have no idea.
I would expect a special syntax for specialization too, just to make things simpler.
Yeah. One thing that people have been debating is whether you should just have some sort of syntax here to hint that there's a template involved, which would satisfy my vague feeling of disquiet over this. But again, watch this space. Right, let's press on. So I've got, by example, check that we think that now is. What was it? Was it in the concept? Yeah, it was, wasn't it? So that's now a template. And test takes float. Also, that's now a template as well. And now I can check on F. Will that compile? Well, if it is of normal type, we'd be looking for user-defined conversions. If it's a template, we'll be instantiating check of float, and check only works with int. So whether or not that code is valid depends on whether it's a constrained template or that's just a regular class name. And that's one of the things that makes me a little worried about this particular syntax. And this is what's it all mean anyway? So we start at the top with this bool check in value, and that's equivalent. You can actually write template in A if you prefer bool check A value, and you can write both of those one after each other in the same translation unit, and that's perfectly valid. You've just defined the same thing multiple times, that's fine. Declared the same thing multiple times, that's fine. I've only got one definition somewhere, but the declarations are completely equivalent. Which itself is equivalent to writing out template type name C and then requires int C. So that, and that are all completely equivalent. And they're all mean the same as that, but they're not equivalent, they're just functionally equivalent. Okay, perfectly clear. Which means if I put that in a header file with any of those, I get an error. I can see this is going to go interesting. Particularly if I start having different translation units, including different header files. So it's a bit complicated, but these three, you can just follow things through and just keep expanding it to the point where you either lose consciousness or understand as appropriate. So the problem I find with the abbreviated form is it's less expressive. It's not giving me, the reader of the code, as much information. The compiler knows it all, but I often don't. The other problem is, one of the restrictions is, if I use this form, it's equivalent to that. There's two ints up here, there's only actually one type. So this int and that int are the same type. There's no way, currently, that I'm aware of anyway, of making them different int types. But down here, of course, I can decide to have int t and int u and have two different types down there. So there's some things I can express with this syntax I can't express with the abbreviated syntax.
But if you were to type def another one, two things, would you ever
Type def, that sees through that. You might have to do some sort of, some sort of wacky stuff. The other thing you can do as part of the same proposal is you can use auto. Auto is the new static, as I'm sure you know. If all else fails, throw an auto in. I'm not so worried about that because auto unambiguously says that this is a template. To me, anyway, if you look at it right. And it matches the way we've gone with lambda in C++14, where you can have polymorphic lambda by providing auto as one of the arguments. So it's obvious to me, looking at that code, that I've written a template. It doesn't make sense otherwise. What does auto mean? It's got to be a range of types. And actually, I'd be quite happy to take just that one bit out of Concepts-TS and put it into the working paper as it stands. But I don't know whether that's going to happen. So I don't know what people think about this concept introducer syntax. Being able to specify just the name of a concept and have the compiler deduce you meant to write a template. I'm fairly happy with writing out the requires form longhand. Yes, it makes the declaration a bit longer, but it's completely clear what you're meaning.
But is there an implication for compile time if you have these
I would hope it would be fairly straightforward. I mean, the compiler is just going to read the syntax you provided. There might be a little couple of extra checks it needs to do. It will presumably make the job of implementing it a bit more complicated, because you've got to code it for all of them and know how to munge one into the other to check for the equivalence. And I think one of the things that would be interesting to come out of the claim implementation is whether they come up with a few cases like that. Because one of the things that often happens when people start implementing stuff in a different compiler is because way back when they made different decisions about how to write simple tables or how to do parse trees or something that's very, very simple to implement in one compiler can become a complete nightmare in a different compiler. Like the way that Microsoft had to basically re-implement their template engine to get brand new templates in, just because of decisions that they've made, probably fairly arbitrary decisions 20 years ago. The biggest experience anywhere, I think, on the planet, probably, of using concepts is Eric's and Casey in the ranges TS. Who's heard of the ranges TS? Anybody? Or sometimes called STL 2.0, which is it's an attempt to reformulate a significant proportion anyway, eventually, of the standard template library using concepts. And they had meetings with people like Stepanov, who came up with the STL in the first place, and other people to kind of brainstorm it, and came up with some good directions for ways forward, and what sort of concepts, what kind of chunkiness you want for the concepts. So for the ranges TS, there's been quite a lot of thought, based in many ways on Stepanov's elements of kind of programming and the idea of what types mean, what's a regular type, what concepts provide the right level of arguing about types and deciding what sort of algorithms make sense. And interestingly, I had a chat with him at the last standards meeting, and he doesn't use the abbreviated syntax anywhere. Early versions of the paper did. Every time he put abbreviated syntax in and he went off to review, everyone said, take it out, put it out in full, so it's clear to the reader what the requirements are and where the requirements are coming from, and what all of the requirements are being evaluated in. So he's got an example, many examples in there. This would be his count algorithm for the ranges TS. You've got existing specification has class input iterator. And you read that and you think, that's code word to the reader. Somewhere else in the standard, it defines the constraints in text on what an input iterator means. So you have a look and it says the template argument should satisfy the requirements of an iterator. So you poke around somewhere else in the standard and find what those requirements are in one of the tables. So of course when you're going into a conceptized one, you replace all this wording with just, it's an iterator. And you and the compiler hopefully both understand what that means and it's enforced.
As long as we have one.
Sorry?
As long as we have one algorithm of that kind.
Yes.
It has a different
Well,
algorithm which usually uses two random operators.
yes, you could have an iterator I, an iterator J, and they would be, that'd be fine. But of course, there's no point just re-implementing what we already have in the standard library with concepts. Well, little point. You want to go a bit beyond that. So he's adding extra stuff. So there's indirect callable relation and other things added in there. But the key bit is all of these extra things are written in terms of named concepts. And both the compiler and the user can read the same thing. So I think it's going to be quite useful. Actually, I did lie slightly. It's slightly more complicated than that because there's another template argument that I've ignored. Where again, it means that the function which is somewhere buried, there it is, count. You can now provide extra arguments and do cleverer things. If you don't care about all that, the projection just defaults to an identity. And the idea behind that, slight off to the side, is it's to allow on-the-fly data transformations. So you can provide to all the algorithms a transformation that takes it from the type you provided to the type you're wanting. So there's quite a lot of nice things that are going to come out of these algorithms. The other thing he decided was earlier versions of the ranges TS used the variable form where you could. And when you realised you needed to have overloading as perhaps some sort of customization point, he would change to use the function form. And after doing this a bit, and I think changing back and forth between variable and function, he decided, just go with function form. It's much easier. You aren't left with the question, why is that a variable concept and this one's a function concept? He's just gone for a single one. So I think that was quite an interesting bit of response as well. But you've still got the need to describe the semantics. So that's a direct quote from the ranges TS. Expressions declared in a requires expression this document are required to be equality preserving, and there's a description of what that means, except for those annotated with a comment. Comment. So again, it's something that you can't actually, no one's found a way of expressing in text to the compiler. It's something that the reader must understand. And I think that's going to be inevitable. There's no real way of expressing full semantics in the language. I'm not sure you want to try. I've got something here I'm going to skip about what happens if you have an overload and it fails, because it's getting very close to the end. A little bit about constraint cost and compile time. Again, most of my problem was just trying to get some examples to compile. I didn't really try big examples to see what the cost is. There's several different costs at play. And one of the things, of course, is you're not typically looking at adding concepts to code base that has nothing. I think you'll be looking at adding concepts to a code base that currently uses things like enable if. So it's a trade-off rather than just extra. And you also have additional cost in that you have to actually write them in the header file, but you've taken away the cost of the documentation. So at kind of meta level, you probably saved a bit as well. I mentioned this about the cost of disjunctions. Here's an example. So I've said this one, it can either have an integral type or a floating point type. And there's a bit of a question over the cost of disjunction, particularly if I have additional constraints below that, because it might be better to put all the ones with and above than have that right down at the bottom to save the compiler doing too much work. Andrew Sutton presented some figures, and he showed that in a template code where he replaced enable if with concepts, he got a sort of double figure percentage speed. I think it was like 18% faster compilation times with concepts, which is encouraging because typically the first version of something doesn't have a lot of the clever tricks that people eventually come up with to make things faster. So it looks hopeful, although obviously by yesterday's keynote, a bit of confirmation bias that's probably looking for those sort of results. It looks hopeful that concepts will be better in terms of compilation times than the current equivalents. But of course people might end up then adding concepts to more functions because they're there. So what the end result will be in terms of compilation times is unclear. And there's a bit of thought going on about whether there's some tweaking needing on the wording for the disjunction case. They're still a TS. They're not in the international standard. You may have seen some of the fuss that erupted in the kind of blogosphere after the last standard meeting about why or why not they are or are not in. I personally was loosely, vaguely thinking probably not in the C++17, but it wouldn't have been over my dead body if they had gone. But my main feeling is there hasn't really been much genuine real-world experience of playing with concepts. Just hasn't been enough. And it seems to be little point in generating a technical specification and then before the ink's dry, voting it into the working paper. I got my BSI copy of the Concepts TS the Tuesday before the meeting in Jacksonville when we voted on whether to put it into C++17. So as far as I was concerned, it's just too close. But it doesn't stop implementers busy putting concepts into their compiler. And that's the thing, as I said at the beginning, that most of us care about. Can I actually use this stuff? There are a few changes that might happen. There's a good blog post Andre mentioned it in his keynote. I think that link worked. The slides will come up on the ACCU website at some point. And there's also lots of things you can do without concepts. If you want to try some of the ideas using enable if, and you can wrap a wet towel around your head and away you go. And my feeling as a kind of conclusion is that you do seem to get better compiler errors. You're giving more information to the compiler about the purposes of this code. It's got the possibility then of actually warning you that you failed to satisfy a constraint in terms that you as a user of the language understand. It also seems easier to write, because again, you're using a language feature designed for this, and the issues about having to come up with dummy template arguments that get elided later on, it's just horrible. Not having to do that is really good. And the ability to do more complicated and subtle overloading about value types and reference types seems to me a definite step forward. The syntax has got a few rough edges, but you know, now's the time. Go out there, have a play, get a copy of GCC 6 when it gets released, if it hasn't been already. Have a chance, play with it, and give your feedback back to the committee on what works, what doesn't work, what issues you have, what users of concepts and writers of concepts find works and find doesn't work. That's it.